All right, so today we're going to talk about exponential functions and what each thing means. So basically we're going to be interpreting exponential equations, okay? And this is before we get to solving, so you just know what each letter stands for, all right? So let's get a color. All right, so here's your equation, y equals ab to the x power, okay? We know it's exponential because there's an x in the x, there's a variable in the exponent. Now each one of these means something different. Your A means your initial amount. It's what you start with, okay? It's where you're starting. Like if I bought a car, what did you buy it for? That's your initial amount. X is the number of changes over a given time, okay? So that's your time. And B is your multiplication factor. It's going to be what we call your growth or decay factor. It tells you if you're growing and it tells you if you're decaying, okay? Now, if B is greater than 1, it is exponential growth, and we can replace that B with 1 plus R and find our growth rate. If B is less than 1 but greater than 0, then we call that exponential decay, and we can replace that B with 1 minus R, and we can find the decay rate, okay? So, for each equation below, identify the equation as exponential growth or decay, find its initial value, and then find the growth or decay factor, and then find the rate, okay? So we're going to be doing a lot for these little problems. So first says growth or decay. Well, if you look, this parentheses is greater than 1, so we're going to call this a growth problem, okay? So there's 1 down. The next one is, what's the initial value? Well, the initial value is going to be our A value, which is right here. So our initial value is 3.34. Okay. Next, it wants you to find the growth or decay factor. Your growth or decay factor is what tells you if it's growth. So my growth, so this is going to be a growth factor, and it's going to be 1.67. Now, to find the growth rate, I'm going to tell you the cheat way, okay? I'm not even going to make it difficult. You subtract 1 and just make sure it's positive. So to find the growth rate, we're going to take the growth factor, we're going to subtract 1, so my growth rate is 67%. Okay? All right, same thing here. Okay, we're going to do the same thing, except I'm going to go to a different page so it doesn't look so clustery, okay? So let's go to a different one and make it a little bit better to read, okay? All right, so let's open a whiteboard. All right, so my problem is, let's go back, new whiteboard. I need to delete some of these. Here we go. So the question is, y equals 8 times 0.54 to the x. So first I want to know, is this a growth equation or is this a decay equation? Well, my B is less than 1, so this is a decay. Okay? Next, it wants the initial amount. What is the initial amount here? Well, the initial amount is your A value, which is right there. So my initial amount is 8. That's what A equals. Okay? Then it wants the decay or growth factor. Well, the decay factor is just the number. The decay factor is 0.54. Now, you actually have to solve for your rate. So it wants the decay rate. Okay? So to find any rate, okay, for exponential, you're going to take that decay factor, you're going to subtract 1. Now, when I subtract 1 from here, I get a negative 0.46. Well, your rate can't be negative, so we're just going to make it positive. Or we'll say 46%. That is my decay rate. Okay? Let's do the third one. The third one was y equals 4.5 times 4 to the x. Okay, so I want to know if this is growth or decay. Well, that 4 means that it's a growth formula. So this is growth because that 4, because that b is greater than 1. My initial value is going to be your a value. So that's my initial value. Is 4.5. So if it was like, how many inches did it start with? It started with 4.5 inches. I was just making something up. All right, now is it a growth or decay factor? It's going to be a growth factor. You have a growth factor. It's what you're multiplying by each time. So like when you've been doing these problems in your head, like when you were younger, that's what you were multiplying by. It's your growth factor. So I am like multiplying each time by 4, okay? And the x tells you how many times to do it. So if it was 4 to the second power, you would do your growth factor 4 times 4 and get 16. Now, this is going to be a growth rate, okay? So we're going to say 4 minus 1, which is 3, okay? So you're going to say that it is growing at a 300% rate, which is fine. It's just weird. Okay? All right, let's go back. Right here. Just trying to figure out where it was. Okay. All right, so now that's looking at the equation and telling me if it is a growth or decay. Now we're going to look at the graph, okay? So when I look at the graph, I want to know if it's growth or if it's decay. So how do you know if it's growth or decay by looking at the graph? You trace it. Is the graph increasing when you trace, or is it decreasing? And remember, it's left to right. So starting here, what am I doing? I'm trying to highlight is what I'm trying to do, to be honest with you. And I don't think it's letting me do it. All right, so we're going to go back to the pen, okay? So I'm tracing it. Elevator's going up. So this is growth. Your initial value on a graph is your y-intercept, okay? Your y-intercept. Where does it cross the y-axis at? It crosses right here. We're going to call that 2.5. So my initial value is 2.5, okay? Number 5, all right? It's going up, so that's a growth. You want your initial value. Where does it cross the y-axis at? It looks like it's crossing at 7 right there. So my initial value here is 7, okay? If you look over here, left or right, this is decreasing, so it's decay. And it crosses at 8. So my initial value here is 8, okay? Oh. All right. So now we're going to scoop the tables. We're not going to worry about the tables. So now I actually want to interpret knowing my word problems, okay? So, and we're going to eventually solve these word problems. I think it's only on Friday. The following 2 formulas are used most often in real life applications. You have your growth and you have your decay. If you look, the only thing that differs in the growth and decay is the plus and the minus. If it's growth, it's a plus. If it's decay, it's a minus. Okay? So, I want to interpret things. Okay? So, let's go. Here we go. So, word problem. So, you got to know what it's talking about in context. It says the growth in a population of a small town since 1996 is given by this function. What is the initial population? Well, that's your A value. Initial population is your A value. My A value is the 1250. So you would say the initial population was 1,250 people. Okay? And when did that happen? Happened in 1996. So you would say in 1996, there was that many people. Growth rate. To find your growth rate, you have to take what's in parentheses, subtract 1, and that gives you my growth rate of 3%. Because I moved that decimal. When you convert a decimal to a percent, you got to move that decimal 1, 2 places to the right. That's how I got the 3%. Okay? Next, determine the population in 2007. Well, if I want to know the population in 2007, I started in 1996. How many years have passed to 2007? Okay, how many years has it been since 1996? Whoops. It's been 11 years. So after 11 years, you're going to plug that into right there, because remember I told you that's your time. So we're going to say 1250, 1.03 to the 11 years. You can just type that in decimals. I've got my calculator right here, so that's what I'm going to do. So after 11 years, the population will be 1,730. Okay? All right. In which year does the population reach 2,000 people? So I want to know, after how many years will it be 2,000 people? So let's look at our graph. Okay, let's take this equation, and I want to see when it's going to reach 2,000. Okay, so when I go to decimals, so I want it to reach, so I want the equation y equals, anytime it talks about reaching something, look at your graph. It's very visual. It'll help you out. We're going to have to raise it to the x instead of the n. But I want it to get to 2,000, okay? 2,000 is right here. Well, I want to get that point. So we're going to type y equals 2,000 because I want it to get to 2,000. Okay, that's right there. That's about 16 years, right? So at 16 years, so it's going to take 16 years, but it said in which years. So I'm going to have to say 1996 plus 16. So 2012. Well, that's the year I got married. 2012 is when I'll reach 2,000 people. Okay? All right, let's do another one. All right, next problem. Okay, so we're going to be interpreting and solving for a couple things. Okay? So this one, let me scroll up. It lets me. Okay, so this one says, a computer loses its value each month after it's purchased. Its value as a function of time in months is modeled. So it's telling me that my time is in months. Okay, that is so important when you're reading these word problems, that you need to understand what it's modeling your time in. So it's saying it's modeling the time in months, not in years, but in months. So it's represented by this. Okay, what's the initial value of the computer? So the initial value of the computer is your A value. So the initial value would be $1,500. Okay, what is the rate of depreciation? So we're going to say 0.95 minus 1. Well, that's going to give us a negative 0.05, but we know our rate is supposed to be positive, so you're just going to make it positive. That's just me giving you the cheat. So convert it back to a whole number, move that, or percent, move that decimal 2 places to the right. So this computer is depreciating at a rate of 5%. Determine the value of the computer after 2 years. Well, we just said it's being modeled in months. So how many months is 2 years? 24 months. Okay? So now I can plug that in, now that I've converted it to what it needs to be, to 24 months. So use decimals, use your computer or your calculator, raise it to the 24. So after 24 months, the computer will depreciate to a value of $437.98. Okay? In which month after it is purchased does the computer's worth fall below 900? So that means I need to make that 900 line and see when it goes below it. So we go back to decimals. I want my lowest, I want to see it at $900. So that's going to be my line that I need to look at. My equation was 1,500. The inside was 0.95. Whoop, 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 whoop. Okay. So when does this get below 900? I'm going to go back home so we can get it reset. We're going to zoom out, scroll to 900. Okay, right here. So after, we'll say 10 months. So after 10 months, that computer is going to get below 900. Okay, so after 10 months. Okay? All right, so now we are going to take and we're going to make an equation given all this stuff. Okay, so it says in 1981, the Australian humpback whale population was 350. Okay, so we need to know that number. It's 350. I don't know what's going on. Here we go. Okay, it increased to about 14% each year since then. Write a function to model this growth. Okay, so y equals, it started out with 350 people. It's growing, so it's 1 plus. Okay, this needs to be converted to a decimal. Move it 2 places to the left, so it's 0.14. And I raise it to the x. So that's my function to model it. So it says use a graph to predict when it will reach 2,000 people, 20,000 people. Well, that's what we just did up here. Okay, I need to have my 20,000 line. Now this can be simplified to y equals 350 times 1.14 to the x. So I need to find when this line reaches 20,000. Okay. So y equals 350, 1.14 raised to the x. And then I want to know when it reaches 20,000. Okay? So we're going to have to zoom out a lot for this one. There it is. So how many years will it take? About 31 years. That's crazy. Isn't that crazy? So it's going to take about 31 years for it to reach 20,000 people. That's crazy. That is absolutely crazy. Okay, to think about that many years in the future. All right. So that is all we're going to do. The rest is going to be for the next lesson when we're actually solving for different variables. Okay, so let me know if you need any more help, but that's it.